Thank you, Dr. Lu, for the introduction and committee. Thank you, everyone showed up here to support. Thanks. My research in my PhD was about synthesis and dynamic mechanical characterization of polymer aerogels. So what are aerogels and why we care about them? Second slide, Dr. Font. Aerogels are highly porous solid materials that basically made by drying a wet gel without shrinking. Typically, a sol gel approach is adopted for making an aerogel. We start with a sol, which is a mixture of solutions, and through a condensation process, nanoparticles are formed, which we call them as primary particles. Primary particles are agglomerated together to form secondary particles, and eventually we have a three-dimensional network of particles filled with liquid phase that we call it the wet gel. Wet gel needs to be dried without any shrinking. Therefore, we have to have a special basically drying technique, which is so-called supercritical drying, to end up to a material called aerogel. Traditional aerogel is silica aerogel, as you can see in this picture. This is a monolithic silica aerogel. They are highly porous, lowest bulk density that you can find, and basically lowest index of refraction, so highly transparent. They are basically they have lowest thermal conductivity compared to fiberglass, 2 to 4 times better. At light vacuum, they can be even 10 to 15 times better, same thickness. So these materials are wonderful and have been used in several applications, primarily in oil industry. One of the pioneers is Aspen Aerogels, who work on pipe installations in oil industry, basically. Recently, Dell has been used aerogel in their laptops. There are some startups for aerogel clothing these days. Has been recently also proposed an approach to make Mars a new place or new home for us using aerogel that is much safer than the other proposals, basically. So, a brief history on aerogels. Aerogels invented by Kistler, 1930. For a few decades, we don't see anything from aerogel just because it's expensive. The manufacturing is costly, especially the way Kistler did it with supercritical drying of alcohol. It was not safe because you imagine you have a pressure vessel filled with alcohol, high pressure, high temperature, and explosion. And one of the first pilots for manufacturing silica aerogel was actually closed just because of explosion. All the way to Dr. Hunt's invention. Dr. Hunt proposed to use basically carbon dioxide supercritical drying, which is carbon dioxide can be at supercritical state at a relatively lower pressure and temperature. Therefore, it is much safer and it's cheaper. Along the way, actually NASA was the main contributor to aerogel to use in their different missions, including NASA rover for thermal management. However, this century was mainly the century for aerogels with emerging new types of aerogels, including metallic aerogels and invention of X-aerogel. We'll get back to X-aerogels later in detail because it's the origin of what I was working on polymer aerogels. But as you can see, the trend is we have a fully inorganic material, silica. We are now facing to more organic polymer aerogels. Polymer aerogels is important because you have aerogel characteristics now combined with plastic-like features, like you have flexibility, like stretchability, to some extent shape memory properties, as you can see here for polyurethane aerogel. So that's a very promising, basically, field to work on. Silicone aerogel was fragile and therefore to extend to see why we have more inorganic. Now I want to talk about the invention of X aerogels. X means cross-linking by polymer. What is happening in X aerogel is you have silica particles in silica aerogel cross-linked with a small amount of polymer. So the polymer is encapsulated, the silicas are encapsulated by polymer coating. As you can see in this figure in part B, we have impact testing by Hopkinson pressure bore test. You have PMMA here, which is a very classical structural polymer compared to X aerogel. And at high strain grade, you can see that the PMMA is completely shattered, but X aerogel can basically absorb the impact energy. This shows that silica aerogel, that classically you cannot even handle it with your hand. It's so fragile. Now with this invention, can be as good as classical impact-resistive polymers, even like polycarbonate. So the question was, if the small amount of polymer is basically causing to make such dramatic improvement in mechanical properties, why not we use purely polymer aerogels? And that was the origin of inventing purely polymeric aerogels from a diverse range of polymer sources, including polyurea, polyamide, polyamide, and so on. And it is cheaper because cross-linking is another step in manufacturing. Now you have one-pot synthesis for polymer aerogel, which make it even basically economically more interesting. Excellent properties, all still with the classical properties of aerogels, including thermal insulator. Now you can achieve like high ductility and stress or a high impact energy absorption. The other thing that I want to focus here is ambigel. Ambigel is an aerogel which is dry under ambient condition. So shrinkage is happening due to surface tension of the liquid phase during the evaporation. So when they do supercritical drying, the surface tension is at lowest possible state. Now you can use a technique which is called sequential solvent exchange to change the wet gel liquid all the way to a state to have a solvent at lower surface tension and lower weight, basically, molecular weight. As an example, you can consider hexane or pentane, and then from that solvent, you can dry your sample under room condition, and that material is so-called ambigel. Ambigel, compared to supercritical aerogel, is much less expensive. The other problem with supercritical drying that we have is supercritical dried sample has a size limitation. At the end of the day, you need to have a pressure vessel to reach that condition that you want. At the current record, the biggest supercritical dryer that you can find is like 30 centimeter in diameter and 60 centimeter in height. But you don't have such a size limitation with ambigel case. This is why in all I have done during my PhD, I focused on room temperature drying just for this purpose, which is more industrially interesting. So the outline of my talk today is going to be 3 parts. Each part is dedicated to each one particular polymer aerogel. First part is going to be polyurea aerogel. I have a sample here for each type of aerogels that I made for. The first polyurea aerogel, my focus was on acoustical properties of these aerogels, on the measurements and simulations. On the second part, I'm going to talk about polyurethane type of aerogel, which is highly flexible, and so it can be an ideal case for basically energy damping applications. And the last thing going to be basically a high performance polymer aerogel, which is good for high temperature applications. So let's talk about the first one. Polyurea is an interesting material, highly scalable, highly multi-scalable. So within the same chemical compositions, it has been shown that this material can be synthesized in a variety of microstructures. You can find conditions just with the control of kinetics of the reaction. You can find conditions to get like basically particle agglomerated, fused particles agglomerated, all the way to fibers, all the way to an interesting structure, microspheres of polyurea embedded into basically polyurea web. This type of a structure is very interesting for acoustical and dynamic characterization. This is why we did basically sound transmission loss measurements on this sample. Again, meantime, here, this is exactly the sample we used for the measurements. So in this experiment, you have basically a long tube made of polyurethane here. The sample is attached at the end of the tube, and we have 3 microphones and a speaker. And so you measure the sound pressure levels at the microphone positions, and you can measure basically the sound transmission loss. Sound transmission loss, by definition, is the sound energy reduction from the sample. Since the sound waves are basically hitting the sample through a normal case, that's why they call it normal incident sound transmission loss. The sound transmission loss of polyurea aerogel is much higher than basically that space loft blanket, which is a silica-based sample made by Aspen Aerogel, and typical acoustic foam. Acoustic foams are in this range of frequencies. Basically, they are showing no sound transmission loss at all. In the other situation, we considered basically a random incident. Instead of having sound waves only hitting the sample through one direction, in this scenario, we have sound waves coming along all directions. In this experiment, what we have is, we have 2 separate rooms. The only connection between these 2 rooms is either a window with area of 1 square meter or a wall. As you can see, those aerogels are attached on the wall, laminated by gypsum. So we have 2 cases. Reference sample is only gypsum. The second sample, which is the test sample, is gypsum and 2 aerogel layer and another gypsum. So random sound transmission loss, also you can see that the aerogels are light material. So having aerogels in between, they'll only add like 20% to the mass per unit area of the sample. But you can see that compared with the reference sample, which is gypsum only, you have dramatic improvement, especially at some frequencies, about 4 kilohertz. You can see 13 dB in case of a big sample, and even 15 dB in the case of 1 square meter. So these promising results needs to be modeled. That's why my first job as a PhD student was to come up with some practical constitutive law and use it for basically to find a predictable way to show how these models can be basically evaluating the acoustical properties of the aerogels. So since the frequency of interest for this special acoustic response is basically leading to a very long wavelength compared to the molecular structure, we adopted an effective medium technique. And since the aerogel is a 2-phase material, we can conclude, basically, we can consider a solid sclera filled with air. We adopted a poroelastic model for this purpose. One of the pioneers in poroelasticity is Buell, and in his theory, basically all assumptions that we can come up to use aerogels are fulfilled, including wavelengths that should be larger than the macroscopic volume. We need to have open cell structure as we have in the case of aerosols. For example, this theory cannot be used directly for foams, which are mainly open, closed cell structure. The other thing is we should not have thermocoupling, basically thermoelastic coupling into the problem. Therefore, with these conditions, we adopted Biot theory. In Biot theory, shortly, we have a stress state on the solid skeleton and hydrostatic, basically pressure state on the liquid phase. They are coupled with a term which is related to the friction force of each basically pore. In here, we consider that the pores are cylindrical shape. Therefore, the Q was basically easy to estimate, to be estimated, basically. In pore elasticity, basically, when you come up with those equation of motions, you end up to basically wave equations. The difference between isotropic elastic materials, you have two longitudinal waves and one transverse waves. The derivations of these equations can be found in a beautiful propagation of sound in porous media book written by Adar. So those wave equation solution can be used to express the displacement field, the stress fields, and also the pressure fields in the liquids in terms of 6 unknown coefficients. Now, in the modeling case, for the case of normal incident sound transmission loss, what we assume that in order to make it simplified, we consider a two-dimensional model. In the first case, basically we have a semi-infinite poroelastic plate submerged in air, which we can consider that has low viscosity. For the solution in the fluid mediums, we consider a scalar potential, so a typical acoustic form of solutions. And so that scalar potential can be expressed in terms of basically two unknowns. Since we are normalize the solution with respect to the incidence wave, we can consider incidence as 1. So we have end up to only one unknown as the reflected wave intensity. And we have a transmitted wave on the other side. And basically combine these two with those 6 unknowns that we had in terms of poroelastic layer, which is our aerogel. We have in total 8 unknowns that can be basically solved. They are ended to a set of equations. By matching the appropriate boundary conditions, you can calculate IT, which is the transmitted intensity, as well as reflected intensity. It should come up with a transmission coefficient. And the transmission coefficient can be later turned to sound transmission loss. Same approach can be adopted for the case of random incidence sound transmission loss. However, in the case of random sound transmission loss, we have 2 more layers. For the gypsum, we consider them as elastic. Because this is a random case, we need to consider the contribution of different angles. Experimentally, it's been shown that you can consider a Gaussian distribution between each angle, to which has been shown that it is more close to the experimental results. That's what we also did. That G function in the definition of transmission is a distribution function that you can use. We use the Gaussian distribution for the contribution of each angle. However, even if you basically consider equally contribution, the results are not very different. However, it's better to use the Gaussian list. For the parameterization, we try to adopt more experimentally measured parameters as much as possible, basically. bulk density, skeletal density can be measured from PET, basically type of measurements. Porosity can be calculated from bulk density and skeletal density. Average pore size can be calculated from intersorption experiments. Static Young's modulus can be adopted using quasi-static compression test. Loss factor was basically we adopted from literature. We didn't measure it specifically, and as well as airflow resistivity for that air structure. Those are also estimated using some empirical formula based on air shear viscosity. A structural factor, since we prepared a code, we could have done some sensitivity analysis. We didn't see dramatic sensitivity on a structural factor. The structural factor is the way that basically pores are connected together. And that's why we picked typical 1, which is mainly used for porous, homogeneous pores when you use a homogenized basically model as what we did. So with these parameterization, we found out good agreement between the pore elasticity theory that we did compared to the experiment. Although in the case of normal incidence, we don't see some characteristics in the experimental. That's why we see some discrepancy, especially at low frequency. But in the case of random incidence, since first of all the sample is bigger and we have contribution from all angles, we have a characteristic in the sound transmission loss, and then we can see that the theory can beautifully basically predict the behavior. So this is the end of the first part of my talk, and now I continue with the second part, which is related to polyisocyanate urethane aerogel, which is a derivative of basically polyurethane aerogel. It's a soft aerogel, a stretchable aerogel. So this material was synthesized based on a monomer, a commercialized monomer, and a diol. The diol that we used is TEG. The choice of diol can help you to tune the mechanical properties of the aerogel. Like we can use different diols, different length for the diols. I'm talking about TEG. The shorter diols, like ethylene glycol, EG, end up to a very entangled sample. Therefore, the aerogel, which is still the same chemical component, is very stiff, so glass transition is high. However, if you use longer diol, as what we did here, aerogel end up to a very softer material. That's what we wanted. We synthesized this aerogel at room temperature and dried it also under ambient condition. Typical carbon NMR can be used to show that the reaction is completed. So this is the fundamental material properties, including the density range, porosity that we got, density as low as 0.28. We focused only on the samples that they are structurally basically reliable. Therefore, that's why in chemistry side, we can go to a lower density, but from mechanical side, that sample is not suitable for us. So that's why we ended up to 0.28 gram per centimeter cubed. It's basically highly porous sample. It's about 77% porosity. Glass transitions are close to room temperature. That's why it's this very soft sample. And it's very flexible with a good recovery. 80% of the strain can be recovered within, like, if you consider the recovery speed that I reported here, it's about 1 millimeter per second. Microstructure of this aerogel at low density is very uniform. Lower density means that we use low amount of monomer. Therefore, the reaction is slower. When the reaction is slower, the materials, the secondary particles can have basically form their own particle. They have time to get along. And therefore, we end up to a more spherical shape with a uniform particle size. However, at a higher density, the reaction is faster. Therefore, the material doesn't have time to form spherical shapes, and you can see more bicontinuous type of a structure. Aerogels, in order to be used outdoor, they have to be hydrophobic. Otherwise, water can basically jeopardize their applications. One of the techniques that we adopted to use to make them hydrophobic is cross-link the outer surface of the aerogel with some chemicals that are not soluble in water. For example, hexylamine is poorly soluble in water. We add hexylamine in the second stage of the washing of the sample.
Okay, I put it on the speakerphone.
Okay, right. So we use hexylamine in the washing steps in the second wash. And as you can see, a small percentage, this is a weight percentage of hexylamine, can change the contact angle from about 77, 80 degrees all the way to 120 and make it basically hydrophobic. This is an approach that we proposed that can be relatively applied to all different types of aerogels. Because this type of hexylamine has a lot of hydrogens that they can form hydrogen bonding cross-linked on the outer surface of the aerogel. We should not use more amount of hexylamine.
Can you get the number on that sheet?
Can you mention that page?
This is a slide number 26.
26?
Yes.
Okay.
Right.
Good.
Okay. And, this is important to use less possible hexylamine because at the end of the day, you should not cover the pores, the outer pores of the aerogel. Therefore, it might change the dynamic behavior. So that's why we stick to very small amount of hexylamine. So next slide. So under quasi-static, tensile properties, next slide, was a study. All 4 samples at 4 different densities, basically characterized under tensile condition. On the right side, you can see a movie using 2D IC. We measure basically the field, the strain field, the strain along X, the strain along Y, and at the same time we can see we have a high degree of stretchability for this sample. We reached 120% tensile strength. This setup has limitation. I think we can go even further. The relationship between Young's modulus and density has an exponent to the power of 6 that shows that this material is becoming very soft when you basically reduce the density. And as you can see, we are like about 265 kilopascal at a density of close to 0.5 with, no, this is Poisson's ratio, I'm sorry. The density is close to 0.4 gram per cubic centimeter, but just basically almost half, making twice lightening of the density, you will end up to a material, very soft material with Young's modulus of only 40 kilopascal. We tested cyclic compressive experiments. We are at slide 28. 2 different scenarios have been basically experimented. In the first scenario, we have basically, we compress the sample all the way to 50%, and then the platen comes back to its original. So that's why we see there is a decent recovery for the sample. And over here, we have the maximum stress at each cycle over the number of cycles. Therefore, you can see the maximum stress is not dropping dramatically in the first 10 cycles. And also the energy absorption. Of course, the first cycle can cause a lot of crack inside the material. Otherwise, after that first cycle, the material is still reliable. In the second scenario, we load the sample and then we unload. As soon as the loading, basically, we have the material is not following the plating, we start to reload it. So it's a load, unload, reload type of experiment, and you can see that this is the material has a shape memory, basically property in itself. It can follow its previous stress state before. This is the loading from the previous cycle, and this is the reloading from the basically the next cycle, and you can see that the material can reach to that state again. Next slide, Dr. We also considered high strain rate properties for this aerogel using Hopkinson pressure bar, and these are different trials regulating the strain rate about 2,500, more or less, with 2 cases, and about 1,000 for 800 basically per second for most cases. And when we average them together, we can see that, slide 30, Dr. We can see that still we have high level of compressibility for these aerogels at high strain rates that shows that these are good impact absorbers. This is the end of the second part. Now jumping to the last part, which is polybenzoxazine aerogel. Polybenzoxazine is an aerogel basically from polymerization of benzoxazine. Benzoxazine is a molecule where you have an oxygen ring, oxygen and nitrogen, attached to a benzene. Benzoxazine is famous for basically high glass transition temperature and low water absorption and high char yield. Generally speaking, polymer aerogels have low glass transitions. Therefore, for practical applications, especially for basically high temperature application, we need polymer aerogels with high glass transitions. This is the reason we decided to work on benzoxazine-based aerogels, and we synthesized, again, ambient dried polybenzoxazine aerogel catalyzed by acid and we had a few basically curing steps at the end. I have the sample here. I ran out of samples, so I started to make. It's a lengthy process because I have to make the monomer. Monomer is not commercialized. This is the sample came off the oven yesterday, basically. Still, it doesn't have. Still, we showed that the material can be synthesized big scale, at big size. This is the biggest sample that I made so far. So the densities that we got, the lowest density is 0.25. You can always compare to density of water. This water is 1, so we're talking about 4 times lighter than water, with 80% porosity, basically. And BET surface areas are in the range of 50 square meter to 70 square meter per gram. Slide 35, Dr. Paul. So the molecular structure, the microstructure of the PBO has in good agreement with N2 sorption. In N2 sorption, based off a particle diameter, we can estimate, based off surface area, we can estimate the particle diameter in the range of 60, 80 nanometers. The SCM, remarkably, also is inconsistent with antisorption. The particles are aggregated on each other. It's a packed. That's why this aerogel is literally stiff, but it's brittle. It has, benzoxazine itself has low water basic retention property. In the form of aerogel, the polybenzoxazine inherently is super hydrophobic. That's why when we put one piece of polybenzoxazine into water, the two ends are sanded. You can see a thin water layer can be trapped, and you can see a typical mirror effect on these basically aerogel surfaces. So no surface treatment, only the sanding basically is happening here. Again, mechanical properties at room temperature studied cause a static compression. Although the material is brittle, but it still can be compressed till like 60% and 50% at basically higher densities. The fracture state is sort of fragmentation. We have cyclic experiments, and similar to polyurethane-based aerogel, we studied basically the peak stress and the apparent modulus. We have a drop in apparent modulus at the first cycle, which is mainly because of formation of initial crack. But after that cycle, we see basically stiffening effect here just because of plastic preconditioning. The material is started to pack on each other. That's why we get a harder surface at the end of like 100th cycle. But the peak stress is basically showing the beautiful relaxation on basically over the cycles of compression. Compared to other aerogels, this material is still stiffer, especially on yield strength. Compared to ex-silica, ex-vanadium, other typical high-performance polymers like polyamide or polyamide, the yield strength of this sample is higher. Properties at elevated temperatures were also studied. These are basically these experiments have been done with instrument machines. So for each sample, for each point, we had to basically do one full cycle, full compression experiment and repeat it at each different basically temperature. We had about 45 minutes temperature soaking for each experiment. We compared 24 hours compared to 45 minutes soaking, and we saw that material at 24 hours temperature soaking has stiffer properties just because material has room to basically expand and basically reconfigure itself to make it more stiffer. But majority of experiments have been done with 45 minutes. The properties including basically compressive strength over temperatures shown that basically we have a slightly stiffening, hardening in the compressive strength at 50 degrees. That might be related to basically air trapped inside the material. But after that, we have a softening in a relatively slower fashion. So for example, you can see that the material at 250 has more or less at lowest density, has more or less like about 30% drop in compressive strength, which shows that this material can be used as high temperature applications. Dynamic properties also used. This is a high fidelity experiment. We used again instrument machine, which is more accurate than typical small DMA machines. In torsion experiment, basically we picked still low temperatures compared to glass transition of polybenzoxazine. Polybenzoxazine has glass transition close to 150, but here we just covered 20 degree, which is room temperature, to about 60 degree. So we did basically torsional test at different frequencies. Grips are attached by glue. We, previous to this sample, we did only the glue to make sure that the glue basically is way rigid, more rigid than the sample. So the compliance of the glue was considered. So the frequency range of interest in the experiment was from 0.1 hertz all the way to 1 hertz. And then we calculated the storage modulus and loss modulus and tan delta, which is the ratios of these two. Assuming basically thermally rheologically simple for the polybenzoxazine, we are able to shift basically storage modulus data to have a frequency temperature shift to find basically the master curve with a reference temperature of 59 degrees. The reason we can do, the reason we did master curve, because measurements at basically middle frequencies is really hard. Low frequency measurement and high frequency measurements are relatively easy. But middle frequencies are really hard. With this technique, we measure only to 1 hertz. Now you can see with shifting of the data over you can predict the properties all the way to 1000 hertz, 3 decades after. We can say that most of single-phase amorphous polymers are thermorheologically simple. And thermorheologically simple means that the polymer has basically similar time dependency at different temperatures, basically. So with this assumption, you can do that shifting. After that, we studied classical thermal characterizations, including thermal conductivity measurements. They are still good thermal insulators. We also showed the transient temperature distribution. This is a hot plate. We put the sample there with observed by infrared camera, real-time speed. So you can see that the temperature can rise, and after 10 seconds, basically the temperature gradient is pretty much as this. So we have a really good thermal insulation still in this material. The length of this sample is about 23 millimeters. This aerogel is still basically self-extinguished. As you can see, we put fire directly on the samples. We don't see any flame getting formed after removing the flame. The carbonized region still has decent structural integrity. Therefore, this aerogel can be used for even internal applications for housing, which we have potential fire risks. The TGA can show that the material decomposition at temperatures in the order of 700 can be only by 50%. So in summary, what I did in my PhD was modeling of polyurea aerogels to explain and show their extraordinary sound transmission loss behavior. I developed polyurethane-based aerogel with high searchability and very good impact properties. And also at the end, I showed polybenzoxazine aerogel as an alternative to other high-performance polymers like polymer. Polymer is very expensive, but this aerogel is relatively very cheap and good candidate for basically thermal conduction and fire resistance applications. This is the thesis publications out of these works. I want to thank Dr. Lu for all he has done to me and the supports the group at large. Dr. Leventis, he helped me a lot in terms of chemistry of aerogels. Dr. John, he helped me with experimental sound transmission loss measurements. Dr. Shuro, who came from a long way today. Thank you very much. He actually was my first mentor in the lab for making the aerogels, and Dr. Dua, which was responsible for all high strain rate measurements. Without him, without all help, these helps, I could have not done these things. At the end, I should thank the agencies who made my life as a PhD student pretty comfortable. So thank you very much.